Christen Fleming is a fellow at the Smithsonian Conservation Biology Institute's Conservation Ecology Center. We've invited Chris here as an expert on mathematical models, statistical analysis, and software packages for difficult to work with ecological data. He's made enormous contributions to big data challenges in movement ecology. So we're really looking forward to hearing from him. So Chris, do you want to take it away? You are still muted.
I'm sorry, I apologize. Thank you for having me. Yeah, so I want to talk about the statistical challenges in analyzing animal movement data. And so where I fit in this story is that a lot of you guys like to go out and collect tracking data on species that you're interested in. And these data are exploding exponentially for various reasons, including Moore's law and lithium-ion battery and GPS, and the fact that no one ever wants to go back to paper maps in their cars. And when you take this kind of data, I develop statistical models and methods and software so that you can turn this into something really rigorous in the output. And you can do that without having to know how to solve a stochastic differential equation or knowing what a stochastic differential equation is, even though that's really what's happening in the background. And so I want to motivate a little bit, why that level of math would be necessary for analyzing tracking data, just very briefly. So you get data that are location estimates with timestamps, say if you're collecting GPS data. And since the locations are sampled discretely in time, the easiest way to analyze these data are with discrete time methods, which you could think about like connect the dot methods. And there are a lot of issues with this, including scale dependence, which has been touched on a little bit today. So if you were to get speeds estimates from this, you'd be assuming that your animal moves in straight lines from one point to the next, which it didn't really do. So the easy models are discrete time models, but the truth is continuous time. And you have some really sparse, possibly erroneous sample of that. So in continuous time stochastic process models, you don't assume to have the truth. You could have a lot of possible trajectories that the animal took, and many would be consistent with the data. And this is necessary to get meaningful estimates and predictions in a lot of cases. So the biggest thing I've worked on is space use estimation or home range estimation. So this is some black bear data. And on the left is a conventional estimate of where the black bear you expect to be 95% of the time in the future. And on the right is the same kind of estimate, but where I rederive this statistical method to leverage a formally selected stochastic process model. And it's way different. The one on the left assumes you have independently sampled data. The one on the right does not. It assumes a movement model. And this is only the first half of the data. And so if you cross-validate in the future and you ask, are these methods predictive? The conventional method is not predictive. It's not useful at all in this case. Whereas my method, you might have thought it was way too big. It's actually a little bit too small when you look at the cross-validation. And so that's why this level of math is necessary, because these tracking data are really complicated time series data. And these stochastic process models can solve a lot of the issues with them, scale dependence. If you had one system, you tracked at 30-minute intervals, and another, you tracked at 1 hour. It doesn't really care about those kind of things. One tracking device, another kind of tracking device, different location error. It can solve all, not every issue, but a lot of issues can be solved with this framework. Things I'm working on right now. One thing I'm working right now is habitat suitability modeling. So this is a taper home range estimate, and it's informed by the taper's selection of tree cover. So this is both a home range estimate and this is a habitat suitability or a resource selection model all together in one. You almost never see people do both of those at the same time, but the only thing that's really stopping you is the right kind of tools, because they're really related tasks. And the things I'm working on right now that I have up and running, and if you've ever done like a habitat suitability or a resource selection kind of analysis, you know there's all these weird questionable statistical issues in this. What do you do about the fact that your data are autocorrelated and these methods are really not built for that? Picking an available area and the fact that your outputs are sensitive to that choice, that seems pretty arbitrary. How many random points do you sample? So I just went through, these are some of the things that I've solved essentially, where you don't have to get into the mud and everything's just kind of cleaned up and done right by getting down to the statistical weeds. Another thing I've been working on is population estimates. So these tracks are individuals, and then with a hierarchical model, making inferences about the population. That's not new, but doing it computationally fast and statistically efficient and easy in software. So I'm a lead developer in the continuous time movement modeling package, and all these analyses I'm showing you come out of that package. Doing that gives you a lot that you can do. So for instance, if you have a bunch of tracked individuals and talking about their population range, conventionally people would take a bunch of coverage areas, a bunch of individual home range area polygons, and they would just merge them all together and they'd say, that's my population range. But you can do something much more rigorous like this, where you can actually get a population distribution with some uncertainty estimates. And another thing, when you have this kind of stuff in place, is you can start thinking about integrating individual tracking data with population data, like eBird, for instance. And the promise that brings is that that the tracking data could potentially mitigate it against these presence-only data and their sampling biases that you get from the fact that you tend to observe birds where people tend to make observations, whereas tracking data follows the animals around in all kinds of places. And then in the future, so those are the things I'm working on at the moment, but 5-10 years out, or the things I think they're really important and need to be tackled. So I talked mostly about GPS and VHF and Argos type data, but there's other kinds of data that are really important too, like detector array data. Like there are around the ocean, like here around Florida, both coasts in North America, all around Australia, and in a lot of lakes around the world in the UK and in the Great Lakes. There's detector array data where you just get a detection event if your tag critter gets near a receiver. And that's a much more complicated kind of data than like GPS data, but it is movement data. And the same thing in North America and growing in Western Europe, this new modus wildlife, small birds, small migratory birds. These you can tag, it's much smaller than GPS tags on your critters, and if they get near a detector, you have an event. And also camera trap data. If you can identify individuals and you have a network of camera traps, that's movement data too. And these are all really similar. And it's possible to build the tools, the models exist. It's possible to build the tools so that people can analyze these kinds of data and get the same things out that people get out with GPS data. It just takes some investment of time and resources to build that software infrastructure. Another big thing I think super important is corridor estimation for lots of reasons, because protecting corridors are really important. There's lots of money going into like wildlife crossings. There's a lot of money and lives lost in wildlife vehicle collisions. I think more Americans die every year from wildlife vehicle collisions and tornadoes, and more money as well lost. But this is like really early, the stuff people are doing. It's really heuristic. We don't even have the appropriate target distributions yet that are really being estimated. The models that are being used are not exactly what you think of for migratory. It's usually like Brownian motion, which doesn't, if you simulate from the models that are being used, it doesn't really look like a migration. And you're missing population variance most of the time too. So there's just a whole lot of cleanup and work that could be done in this area that I think a ton of people would appreciate. And just for small things, I could list a whole bunch of things and go into any of these topics in a ton, but like integrating accelerometer and tracking data could benefit a lot of different ways in terms of behavioral modeling, in terms of battery life efficiency. I talked about these detector array kind of data, and there's some work that can be done to get those up to speed with like GPS type data. The same can be said of light level geolocator data for small migratory birds. A lot of work's been done on that, but more work could be done to get that up to speed, where you could just feed that in like it's any other kind of data, and just maybe the computer time's 10 times longer or whatever, but you could still get out all the kinds of things that you want. And also resource selection models. So I think I'm working on this, but there's a whole lot more to do there in terms of like continuous time resource selection models. That's like a whole talk there. And there's just a ton of things. And my closing thoughts are that there's just a whole bunch of statistical challenges because these are really complex data. And but there's so much more information to squeeze out of these data. Not only like future data, these data are accumulating exponentially, but just the data we already have, there's a lot more in there. And I think what there needs to be is it's a combination of research and then making sure everything gets implemented in software, because the level of math that's required for a lot of these things, you gotta have it implemented in easy to use software. That just has to be what needs to be done. The research alone I don't think is going to cut it. So thank you.
Thank you so much, Chris. That was super interesting. We hear a lot at least in our circles about integration of technologies being like the big emerging challenge and like area of focus, and we don't often hear as much about the integration of data sets and from the statistical perspective that you're talking about. So thank you for that. We have quite a few questions for you. I'll kick off with reading out some from people without mics. Neil asks, an easy one, where do we find the tools to run these analyses?
Yeah, so the package I developed is called CTMM, and it's on CRAN, and there's a development version on GitHub that has all these resource selection function features I showed. Those are in the development version on GitHub. And then if you haven't learned R, or if you're like a manager that's never going to learn R, we also have a point and click CTMM web that you can use, and it's a GUI kind of tool, and it has all the main things in there for space use estimation and speed estimation and whatnot.
Point and click got some nods. Second question, do you think we could inform stochastic movement process between GPS locations with other sensors on the animal, like accelerometers and heart rate monitors, to be able to derive the most probable complete track?
Yeah. So I think that's one of the big things you can do. And what you need for that is you need continuous acceleration models, which you don't need for GPS data, because they're not, even with like 1 Hertz GPS data, you just don't need that. But you do need those for the accelerometer data. And you need behavioral switching models, because animals shift between different movement behaviors or gaits. And when you have those two ingredients, and then you integrate those two data sources together, you can get much more accurate estimates of where the animal is moving and what its movement behavior was at the time. and you can do all kinds of stuff with that, including getting really high precision estimates of where the animal's going.
Awesome. Rob, do you want to jump in?
Is it me, Rob?
Yeah.
Hi, Christen. Thanks for the talk, and thanks everyone for those great. I have a million questions actually for everybody, but my question was in your graph where you showed the territory that you had mapped for the bear, and you showed you had some cross validation data. I just wanted to clarify that that's actually real GPS data from that bear, right, that you used. Yeah, so your model actually, as you said, was maybe a little small. And I love the comparison with the classical or conventional model to the left. Great job. Yeah,
we got our hands on every range resident tracking data set we could in a short period of time, and we did a big comprehensive analysis to really prove, because I developed these methods and a lot of people are like, okay, there's 50 home range estimators on the market. Yours is just one of them. It's like, no, it's not the same. So we did this comparative analysis to really show that you have to account for the temporal autocorrelation in these tracking data to get good predictions.
Great stuff. Thank you.
Thank you.
Rand Nathan, do you want to jump in next?
Yes, Chris, hello. Yeah, you made so wonderful contribution to the statistical analysis of movement. I just want to say that this distinction between discrete and continuous time analysis of movement is surely very important in the times of Argos and other low resolution data, but I think now that we can sample very accurately every second or so, it's not a big issue anymore unless you tell me why it is.
Well, so you want your outputs to be things that are based on a continuous time model, even if you have high resolution data. So if you have location data, something like speed is derived from the time derivative of location. So, and if you don't have a model that has that buried in the model, and you just take like distance divided by time, and you don't like filter out the location errors and whatnot, you can get all kinds of weird things out in the end. And what you really need to estimate something like speed is you just really need a continuous time model and a location error model with high resolution data. So I think the need for that doesn't go away. It's just the benefits change when you go from low resolution to high resolution. And I think whether or not you're going to have high resolution data on your species and on your taxa really depends a lot. I mean, I think coarse resolution data will always be here. It's just going to be moved to a different taxa. And your taxa will go from coarse resolution to high resolution, but then it becomes someone else's problem down the line. So just kind of fixing that and having an all-encompassing solution, I think, is pretty useful. But I'm not against discrete time methods. It's just, when you can have irregular sampling and gaps in the data and all sorts of issues that a lot of people have, I think that's the rule rather than the exception. Then the continuous time methods are just really useful for taking care of that.
Thanks.
All right, I'm going to, there's a couple more questions, Christian, but I think you can pick them up in the chat from Aurora and from Tig as well. So do you want to just have a little look through the chat while Mackenzie is speaking and respond to people there? And we'll pull you back for the discussion in a little bit.